All right, so I'm recording. Okay, so we're going to continue talking about Duhamel's principle. And this is really just a method for solving the wave equation used in the case of forcing. So if we have the initial value problem for the wave equation with some arbitrary forcing function capital F, and we'll start with homogeneous initial conditions, and I'll talk about at the end how to just use linearity to just superpose this solution with D'Alembert's solution. Then remember that Duhamel's principle says that essentially what we want to do for a particular point, which I'll call x0, t0 in the xt plane, we want to look at the domain of dependence, which emanates from this point that's encircled by this line that we'll use the line integral over, that has normals that we can compute directly. So just a reminder, so this point is x0, c, t0, and it's, along t equals 0. This is x0 minus c, t0, and then t is equal to 0 at this point. And these are essentially just the characteristics that are coming down from this point. And so that triangle gives you the region that your solution should depend on at that point. Okay, and in particular, the thing that's new here is that it's going to depend on forcing there. So it's not just like you're propagating initial conditions anymore. There's new information basically at every point that's introduced by the inhomogeneity. And so key to using a little bit of vector calculus is to know the normals. So I'll just write down the normals along each segment of this line integral again that we had written down last time. They're just reflections of each other about that point. Sorry, I'm just sort of squeezing this in here. And then the normal here is going to point downward. Okay, and I'm making these unit normals so that I can more readily apply divergence theorem. Okay, so what we said last time is that we can kind of take this PDE and integrate it. That's the idea. We want to somehow integrate this PDE, but we have to do that very carefully because we're working in multiple dimensions, and we want to only integrate around the region that this solution depends on. Okay. So what we said is to note that if I take the gradient with respect to x and t and dot it to get a divergence of c squared ux and minus ut, then this is essentially equal to dx dt dotted with c squared ux minus ut. This is equal to c squared uxx minus utt, and the PDE just tells me that this is equal to minus f of x. Okay, so the useful thing here now is that I have that minus f of x, which minus f of xt, which is something that I know, is equal to the divergence of something. So the thing minus f of xt, I can just integrate, take a volume integral, for instance. And the unknown thing that I have, well, at least I can apply the divergence theorem to have a more convenient form of this integral. Okay. So what I'm going to do is I'm going to use the divergence theorem, okay, in order to integrate this equation that I have now. So the idea then is that I'm going to call this region Q. This whole region of dependence I'm going to call Q. So I don't have to write out something complicated. I'm just going to integrate minus f of xt over that region, okay, which lives in x and t. So this is equal to the volume integral of the divergence of c squared ux minus ut dx dt, okay? And then the divergence theorem tells me that this is the same as taking a line integral around the boundary of Q of the normal along each segment dotted with c squared ux minus u sub t, okay? So essentially, remember the divergence theorem tells me that the outward flux is equal to the volume integral there, okay? So this thing here, remember this is a line integral, okay? And I'm going to label these different lines just so I can keep track of them. This will be line 1, 2, and 3 here in Roman numerals. And so I'll just break this up into the integral along line 1, 2, and 3 of the normal along each of those, which I have already. And then my vector involving these first derivatives of my unknown solution, okay? So I got 3 regions to take care of, okay? And I've made some progress essentially because if I can integrate these things up, okay, and I do it in a way where I can just extract u from this integral, okay, then perhaps I can rewrite this whole integral equation in terms of something just involving u and then an integral over f, okay? So what I'd like at the end of the day is u expressed in terms of some integral of f, okay? And that's what I'm hopefully gonna get, okay? So what I'm gonna do next is I'm just gonna work out these line integrals along each of these segments, okay? So that's what I'll do on the next page. So let's start now, okay? So the first integral, right? Remember I have a normal, but my normal here is just minus 0 and minus 1 here, right? Let me just draw a little triangle over here. Maybe I can just squeeze it over here, just as a little reference here, right? So here's my 1, my 2, and my 3, and I have my normals popping out of there, okay? All right, I'm not gonna rewrite everything, but let's just have that there in the top right corner as a reminder, okay? So this is 1 down here, right? And remember, there's an orientation that I've chosen to that line integral, okay? And where does it go from? Well, it goes from, oh, sorry, I messed that up. It goes from the leftmost x value here, which the leftmost x value here is x0 minus ct0, up to the rightmost x value, which is x0 plus ct0 of c squared ux minus ut dx, right? And because it's a line integral, I'm only integrating in 1 dimension. And in this case, it's parameterized simply by just movement in the x direction, right? That's where that segment sits, okay? So in this case, because of the initial conditions, okay? What do I know? Let's go back to my initial conditions. Well, I know that u is 0 along t equals 0. I know that ut is 0 along t equals 0. So that means ux is 0 as well. So everything that lives in here is just going to be 0, okay? So this integral is going to be 0, okay? So that's the easiest one to start with, okay? It just vanishes. So that tells me that hopefully I'm going to get non-trivial contributions along the other segments of this triangle, right? I think Sachin asked yesterday, well, what if you have, inhomogeneous initial conditions? Well, then you would get non-trivial contributions here, right? And I think if you worked it through, you would probably end up with, essentially what you get from D'Alembert's solution. But we have another way of sort of massaging that in after we do this homogeneous initial condition case. Okay, so fine. So we're done with segment 1. How about segment 2? So again, this is going to be a line integral, okay? And we have to think a little bit harder about this. So our line integral in this case, right? It has a dt component and a dx component, okay, that contributes to the differential along the directional line, right? I mean, in this case, it's going up and to the left, but I'm just sort of sketching this here, right? So remember, for line integrals, then, we have to parameterize the line, all right, because we need to make it one-dimensional. And so L of S is going to be our parameterization, okay? And the formula for movement along this parameterized line, so the value of L in particular that I get for a particular value of my parameter S, right, is going to be given by this arc length formula. So I get dt ds squared evaluated at S prime plus dx ds squared S prime ds prime. Okay, so I need to sort out what t and x are as a function of my parameterization S. So what's a parameterization I could pick? Well, remember, this is the line that goes from here up to here, right? It starts out at the point x0 plus ct0, 0, and it goes all the way up to just x0, t0. And so, S should be increasing as I'm moving up to the left, okay? So x of S, then, I'm going to define as x0 plus c t0 minus S, okay? And then S is going to terminate at t0. That's going to be my highest value of S along this parameterized segment. And t of S here, it can just be S, okay? So I'm just assigning S to be my parameter here. Remember that my normal here, this is this direction that's sticking out here, is going to be, sorry, let me write this a slightly different way from how I did before. Is going to be just the normalization factor and 1 and C, okay? And I'll just put a note up here that S goes from 0 to T0, okay? And so dl ds, in this case, if we work it out, okay, I won't go through all the steps in the integration, but we get 1 plus c squared in this case, okay? So when I set everything up, right, and I have to compute this line integral, then what I get is the integral from S0 up to S, okay, of n hat dotted with c squared ux minus ut dl ds, right, now integrated with respect to that parameter, okay? And in particular, I can run that parameter from 0 to t0. I know what my normal is, right? And then this factor here cancels out with the factor that I get from dl/ds. So this simplifies down to c squared ux minus ut ds, okay? So within these functions ux and ut now, I'm going to have my us and my ts, okay? So the way that I sort of project this down to just a parameterized integral is that I just have my parameter be the sole variable that I'm changing in this integral, okay? So when I take this dot product and then I plug in these formulas for x of s and t of s, what I get is c multiplied by this integral 0 up to t0 of c ux x0 plus c t0 minus s, right? Because this is just the way that I've parameterized x and t now, minus ut x0 plus c t0 minus s ds, okay? So now what do I have? I have an integral over, two-dimensional functions, right? But they're each just parameterized by that one variable or parameter s now, okay? So it turns out that this expression here, right, it can just be written as the negative total derivative of u with respect to s, okay? So I can rewrite this as just minus du ds x of s ds. Why can I do this? Well, because du ds is equal to u sub x of dx ds, okay, plus u sub t dt ds, which is just going to be 1, right? So I get minus cux plus ut, okay. All right, so from what was something very complicated, right, now I can use this fact that I've parameterized the x and t variables there in order to get a much simpler expression, which is now integrable, okay, just using fundamental theorem of calculus, okay? So if I do that, then I'm just going to end up with u evaluated at the limits of s, okay, which I'm going to write down now. So I end up with that's equal to minus c u of x0 t0 minus u of x0 plus c t0 evaluated at 0, okay? And again, because I had homogeneous initial conditions, I know that that second term there is just going to be 0. So I can write this as minus c u x0 t0. So again, this is going to be equal to 0 because of the initial conditions. Okay? So that's you know, a lot more work than the first one, okay? But the steps were essentially just write out that line integral. You have to use this arc length formula. So that, you know, requires a little bit of calculation up front. You just plug it in then into your line integral formula. And then the important observation is that the combination of derivatives that you get from this normal dotted with your vector of derivatives is a total derivative with respect to your parameter, okay? And if that wasn't true, then, you know, you would have a harder time computing that integral, okay? So as you might imagine, the next part is, you know, kind of a reflection of the line integral that we just did, right? So now we're going to have to take the line integral along the left part of this triangle here, okay? So maybe we should expect to see similar things, okay? So, so part 3 now is again taking a line integral where we have to worry about parameterizing x and s, right? So, or sorry, x and t. So x is going to be, in this case, x minus cs, okay? Where s goes from 0 to t0. And t of s, that'll be t0 minus s, okay? So remember, that's this line here, right? It's going from x0, t0 down to x0 minus c t0, 0, okay? So that's how we get a nice parameterization of that. We can write out our line integral again. It's going to be the normal dotted with c squared u sub x, u sub t, dl. This is equal to the integral from 0 up to t0, minus 1c dotted with c squared ux minus ut ds, okay? And I'll just say that the intermediate steps are similar to before, right? We compute that arc length formula, we compute the derivative, we dot, and we get that cancellation of the square root of 1 plus c squared term. When we take the dot product again, we get something that looks very similar to the case of the second segment, except that we have some sign reversals in this case. And this is integrated up with respect to s, okay? As before, okay, we can now, again, make the observation that this whole thing is the negative total derivative of u with respect to s, okay? So if I differentiate u with these arguments with respect to s, okay, then I'm going to get, you know, a negative term coming out, popping out of each. I'm going to get an additional term of c coming out in the case of u sub x. So I need that negative term, so that cancels out the negative that I had before. Now I can use just fundamental theorem of calculus to integrate this up and just evaluate it at the limits, okay? I'm going to get this additional term now of another term of minus u of x0, t0. This thing here, right, is going to be 0 because of initial conditions, okay? And I'm left with minus c u of x0 squeezing it in there a little bit too close. I'll write it down here. Yeah. Minus c u of x0 t0. Okay. So that's all the steps together. That took us a little while. Okay. So the line integrals now, we have 1 was 0, 2 was minus cu, and 3 is minus cu. So we end up with minus 2c u of x0 t0. Okay. And what do we know? We know this is equal to minus q f of x prime s prime dx prime ds prime. Okay. So we have our solution. If I replace the x0 with x and I replace the t0 with t, then I end up with 1 over 2c, the integral of q of xt now, because that thing is going to change as I change my value of x and s, or x and t. And I'm going to have to integrate over that triangle. Okay. I can write this out more fully as 1 over 2c integral from 0 to t, integral from x minus c times t minus s, x plus c times t minus s, f of, let's say, y s dy ds. Okay. So our region, right? Again, it's going to be a triangle. I've just changed that. I've dropped the 0 subscripts there. It's going to be a triangle like that, okay? Where this point here is going to be x minus ct 0, and this will be x plus ct 0, okay? And this is my q of xt now, okay? So that's why the domain of dependence is so important, again, because it determines the solution that I get both in homogeneous and inhomogeneous forms of the wave equation. Okay, so so that's just one way of deriving Duhamel's principle. If you look in Shear and Levy, they use an alternate derivation and there's a homework question about that, where essentially you convert this into, basically from an inhomogeneous PDE to a homogeneous PDE, where you basically put all of the inhomogeneity in as initial conditions for a series of wave equations within a homogeneous initial conditions, okay? And then you can use D'Alembert's formula. And this thing here, I mean, it should sort of remind you a bit of what's going on with the integral over the psi function that represents your initial velocity in D'Alembert's formula. This should look reminiscent of that. It's sort of like what we did is we said, well, at each point in time, I'm going to take slices, and I'm going to say that's my new initial velocity, and I'm going to integrate that over all time. Okay, and that's essentially the alternate way of deriving Duhamel's principle from D'Alembert.